Nobody cleared this, but forget it, let's go. Number 10. Gravity anomaly. You are standing on a ridge of cold, lunar rock, and the ground tugs at your instruments a little harder than it should. That extra pull is small, enough to shift a decimal on a gravimeter, but it refuses to go away. Grail mapped the moon's gravity field across thousands of orbital passes. Maria Zuber's team found patches near several Artemis 3 candidate regions where the density numbers do not match the surface. Something heavier is hiding underneath. The leading explanation is impact melt, molten rock that pooled during a collision and cooled into a dense plug below the regolith. Another candidate is a buried slab of iron-rich debris from an asteroid that broke apart on impact and never resurfaced. Geologists have modeled both, and neither fully accounts for every patch. That gap between prediction and measurement is exactly what draws mission planners to these spots. For engineers, the gravity signal is a warning. Set down above a dense block, and the lander could settle on an uneven foundation, or the drill could hit resistance at shallow depth. For geologists, the same signal is an invitation. Dense material at shallow depth means the subsurface near the landing zone is not a uniform blanket of dust. It has structure. And structure means history. A compacted layer could have formed a natural cap over softer ground early in the moon's life. Anything trapped beneath that cap would have been shielded from solar wind and micrometeorite bombardment across an enormous span of time. The material below might look nothing like the weathered gray powder on top. Settling this requires seismometers on the ground and a short core pulled from the ridge. The map says something dense is sitting there. Now someone has to go find out what it is made of and how long it has been sealed. Number 9. Subsurface radar. Pulses of radio waves leave an orbiter, pass through the dust, and bounce back carrying a hidden picture of what lies below the surface. When the echoes come back sharp and layered, that means a sudden material change underground. Over several Artemis candidate zones, scientists found the same strange echo on repeated passes. The signal is bright and flat. Not the messy blur you get from loose, mixed regolith. Something down there is reflecting cleanly as if a hard surface is sitting under a softer one. Buried ice slabs could produce that signature. So could compacted rock lenses or debris from an old impact that settled in neat horizontal layers. A roofed void that later filled with fine sediment would also return a clean echo. The important detail is that multiple viewing angles and different instruments keep registering the same reflector. At that point, you stop blaming instrument noise and start planning a drill site. What makes this more than a geology footnote is what researchers call the lid scenario. A compact reflective layer sitting above softer material could act as a seal. Anything trapped beneath it would be protected from the relentless churn of the surface for as long as the lid held. If that lid exists, what is underneath could be remarkably well kept. Volatiles and chemical traces from collisions that happened before life appeared on Earth could still be locked in place. VIPER and the planned seismic packages were designed precisely for this kind of target. A short drill core would show ice crystals or glass shards and settle the question in minutes. The echoes point down. The drill goes next. Number 8. Hydrogen spike. Why does a patch of the South Pole that should be dead quiet sing on every orbital detector that passes over it? Neutron detectors measure how neutrons slow when they interact with soil. Where hydrogen is present, the counts dip in a specific recognizable way. Lunar Prospector first mapped those dips in 1998. Then LRO's LEND instrument, led by Igor Mitrofanov, confirmed them with higher resolution. Several of those hydrogen hotspots sit directly over candidate Artemis landing regions, and the numbers are not subtle. The standard explanation is water ice trapped in permanently shadowed craters where temperatures drop below -200 degrees Celsius. That ice might be mixed into the dust grain by grain, or it could form compact layers that would be easier to extract. But the part that caught researchers off guard is how sharp some of the spikes are. They are tighter and more concentrated than models predicted, and they repeat across independent passes. If the hydrogen is bound inside minerals, rather than frozen as ice, the chemistry story shifts. Mineral-bound hydrogen points to different delivery mechanisms and different ages. If the hydrogen is free water ice locked in clean layers, it could hold a chemical record stretching back to the heavy bombardment era when comets and asteroids were slamming into everything in the inner solar system. The gravity anomalies from number 10 could be related. A dense cap sitting over ice-rich ground would explain both a gravity spike and a hydrogen spike in the same zone. Two instruments and two independent signals pointing at one possible answer sitting a few meters below the regolith. VIPER's neutron spectrometer and drill were built for exactly this target. The numbers have been consistent for over 2 decades. What remains is finding out what form the hydrogen actually takes. Number 7. Impact plume cocktail. In 2009, NASA aimed a spent Centaur rocket booster straight at Cabeus crater near the South Pole and let gravity do the work. The booster hit at over 9,000 kilometers per hour. The L-Cross spacecraft followed 4 minutes behind, flying through the debris cloud with its spectrometers wide open. Anthony Colaprete's team pulled the plume apart molecule by molecule. They found water ice at roughly 5.5% by weight. That alone confirmed what hydrogen detectors had been hinting at for a decade. But the water was just the beginning. The plume carried carbon dioxide and carbon monoxide and methane and ammonia and hydrogen sulfide and ethylene and traces of mercury and silver. Each compound acts as a chemical timestamp. Carbon species point to organic, rich impactors. Sulfur compounds suggest volcanic outgassing or a specific class of meteorite. Mercury and silver matter here because they vaporize easily and migrate toward the coldest spots on the moon. Finding them alongside water means the cold trap in Cabeus has been active and collecting material for an extraordinarily long period. Peter Schultz studied the plume dynamics and found that the ejecta came from layers, not a single uniform deposit. The crater floor had been collecting and freezing deliveries from across the age of the solar system, stacking them in sequence like pages in a book. For Artemis crews, Cabeus and similar permanently shadowed craters near the candidate landing zones are proven volatile sinks. An astronaut with a sealed core tube and a portable mass spectrometer could pull up chemistry that has been locked away since before anything was alive on Earth. That is the kind of record you do not get to open twice. Handle it wrong, and the data is gone forever. Number 6. Unusual albedo streaks. Most of the south polar surface is the same tired gray, so when a bright ribbon or blotch appears in high-resolution orbital imagery, it gets flagged immediately. These patches reflect light differently than surrounding ground, and the difference is not a trick of angle or exposure. It shows up in image after image, pass after pass. Spectrometers on LRO recorded uncommon mineral signatures in several of those bright zones. The Artemis, 2 flyby images added more data points. Something in those patches has a different composition than the regolith around them. The most conservative explanation is fresh material. A small impact or a recent landslide can peel back the top layer and expose rock that has not yet been darkened by solar wind bombardment. That rock would look brighter for a while until space weathering catches up. Another possibility is transient frost, thin volatile deposits that brighten the soil when thermal conditions allow. A third is a mineral deposit with unusual reflective properties left behind by processes that are no longer active. Which explanation is correct matters more than it might seem. If the bright streaks mark recently exposed subsurface material, a short scoop could return rock that is far less weathered than anything on the surrounding surface. That kind of rock gives you a cleaner chemical red. If the patches are frost, they become targets for resource mapping. And if they turn out to be remnants of an older deposit that somehow resisted weathering, they might hold chemistry from a period that everything around them has already lost. Orbital data brought us this far. The last step needs contact with the ground. Number 5. Skylight hints of voids. In orbital photographs, a small round shadow punctures the planes and looks like a dark eye staring into the ground. Those dark dots are skylights, places where the roof of a lava tube or underground cavity collapsed and left an opening. LROs, stereo cameras, and laser altimeter have measured the depth and slope of several of these holes. The pit in Mare Tranquillitatis is roughly 100 meters across and drops into darkness that cameras cannot fully resolve. Similar features appear near Marius Hills and Mare Ingenii. Planetary geologists read them as access points to tunnels carved by flowing lava billions of years ago. On Earth, caves protect sediments and delicate artifacts from surface erosion for thousands of years. On the Moon, the protection would be far more extreme. A tube beneath the surface is sheltered from micrometeorite impacts and from solar wind stripping and from the temperature swings that grind away volatiles and fragile compounds on the open regolith. Any layered deposit inside a tube is a candidate for exceptional integrity. The same kind of radar reflector discussed in number 9 could exist inside a tube wall sealed beneath a stable roof instead of open ground. If intact layers survive there, they would carry chemistry that the surface lost long ago. The challenge is access without destruction. A small robot lowered on a lightweight tether can photograph the interior and take laser scans before anything is disturbed. A compact seismometer placed at the rim would listen for echoes and reveal whether the cavity is empty or layered or filled with settled debris. Tiny pneumatic cores can take short samples from the tube lip and test for trapped volatiles. Engineers will go slowly. A collapsed roof can release fine dust that fouls instruments and suit seals. Robotic scouts map the floor first. Astronauts come second with clean protocols and sealed core tubes. If the walls hold what the radar hints at, those tubes could be the best kept records on the moon. Number 4. Seismic whispers. In 1969, Gary Latham's team placed the first seismometer on the lunar surface during Apollo 12. What they heard surprised everyone. The moon rang. When the ascent stage of the lunar module was deliberately crashed, the vibrations lasted for nearly an hour. The signal built slowly and peaked and faded in a pattern that no one had predicted. That long ring told scientists the upper crust was dry and fractured and layered in ways that scatter seismic energy rather than absorb it. Apollo 14 and 15 and 16 added more stations, and over the following years the network recorded thousands of moonquakes. Deep quakes and shallow quakes and thermal quakes triggered by sunrise and impacts from small meteoroids. Each event painted a slightly clearer picture of what sits below the surface. Those instruments were shut down in 1977. For nearly 50 years, the moon has been silent to us. Artemis changes that. Planned seismic packages will go down near the South Pole, much closer to the candidate landing zones than any Apollo station ever was. The method is powerful. Controlled thumps from a mechanical source send waves into the ground. Those waves reflect off layer boundaries and return to sensitive receivers. By comparing travel times and wave shapes, scientists build a depth map. A fast, bright return means a hard layer. A slow, damped return means loose fill. If the profiles show a thin, hard lid sitting above a denser base that matches the radar signature from number 9 and the gravity signal from number 10, 3 independent measurements converging on the same layered structure would be very difficult to dismiss. Seismic work is patient and unglamorous, but it is the only tool that reads structure at depth without digging a single hole. If the South Pole has layers, these instruments will hear them before any drill bit turns. Number 3. Ejecta from the deep moon. Pick up a rock from a slope near the South Pole, and it might look ordinary until a spectrometer tells you where it actually came from. Some of those rocks originated kilometers below the surface. Large impacts in the moon's early history dug deep. The collision that formed South Pole Aitken Basin was powerful enough to excavate the lower crust and possibly the upper mantle. The debris was flung outward and landed in ejecta blankets that spread across surrounding terrain. Orbiting spectrometers have found signatures of olivine and specific pyroxenes in ejecta near candidate Artemis landing regions. Dan Moriarty's compositional studies confirmed that these minerals form deep below the surface under heat and pressure that the upper crust never experiences. That means the ground near certain Artemis sites carries fragments of the deep moon sitting right on the surface. A lander touching down in the right ejecta field can scoop pieces of the lower crust without boring a kilometer. Those fragments carry information the surface has long since surrendered. Deep material that was buried and then quickly sealed under fresh ejecta would have been protected from space weathering. If volatile traces or rare isotopes survived in those fragments, the chemistry could record conditions from the moon's first few 100 million years. The plume cocktail from number 7 proved that cold traps can lock in compounds for enormous stretches of time. Ejecta blankets may do something similar through burial rather than freezing. The rules for collecting this material are strict. Keep sites clean and avoid exhaust contamination from the lander. Record exact context before touching a rock. Prioritize small targeted collections over broad disturbance. The goal is not the biggest rock on the slope, it is the clearest chemical story from the deepest source. Number 2. Polarization echo. A radar instrument on LRO sends circularly polarized pulses toward the South Pole and reads the spin of the returning signal. That spin tells scientists what the beam encountered below the surface. The instrument is called Mini-RF, and it measures something known as the circular polarization ratio. When radar bounces off loose, dusty ground, the ratio stays low and predictable. When it bounces off rough, rocky surfaces like fresh crater rims, the ratio climbs both inside and outside the crater. But in a handful of permanently shadowed craters near Artemis candidate zones, the pattern breaks. The ratio spikes only inside the crater floor, where temperatures stay below 100 Kelvin and sunlight never arrives. Outside the rim, the signal is normal. Paul Spudis and his colleagues studied this interior-only signature across Shackleton and Faustini and other south polar craters. The spike does not fit rocks or roughness alone. If wall collapses had caused it, the high ratio would appear on both sides. It does not. Scattering models say the pattern fits ice distributed in the top few meters of soil. Cross-reference this with the hydrogen spikes from number 8 and the picture sharpens. Two completely different instruments, one counting neutrons and one reading radar spin, are flagging the same craters for the same reason. Add the thermal maps that show these floors never warm above the threshold where ice sublimates and three independent lines of evidence converge. For Artemis crews, the next step is ground truth. A small rover carrying a sounding antenna and a drill descends into a shadowed zone and tests whether the anomaly corresponds to actual ice layers or to an unusual rock texture nobody anticipated. If layered ice is there, it becomes a frozen chemical archive that could be older than anything still intact on Earth's surface. The radar keeps pointing at something real. What comes next depends on what the drill brings up. Number 1. The pattern. Not a single instrument. Not a single clue. The real discovery on this list is the convergence. Gravity maps flag dense patches below the candidate landing zones. Radar echoes show a hard reflector beneath softer ground in some of those same areas. Neutron counts dip where hydrogen concentrates. Polarization ratios spike inside permanently shadowed craters. A deliberate impact into Cabeus pulled up a cocktail of compounds that should not all be in the same place unless something has been collecting and freezing them for an extraordinarily long time. Bright streaks on the surface hint at material that weathering has not yet reached. Skylights open into tubes where conditions favor long-term integrity. Seismic models predict layered structure at depth. And ejecta fields carry fragments of the deep moon right where astronauts can pick them up. Any one of these by itself could be explained away. An instrument glitch or a modeling error or an unusual geology that mimics something more interesting. But 9 independent lines of evidence from different instruments on different missions built by different teams do not all malfunction in the same direction. The pattern is what matters. Artemis. 2 crew observations and orbital logs and ground-based monitoring have added more data points to the map. Scientists are trained to resist premature conclusions, and that discipline is what separates this from speculation. Nobody is claiming buried structures or alien artifacts. What the data says is quieter, and in some ways more profound. The south pole of the moon has been collecting and sealing material from across the age of the solar system, and we are about to open it for the first time. The operational priority is careful handling. Robotic scouts go first with strict contamination protocols. They photograph and sniff with mass spectrometers and take shallow cores in sealed tubes. Record everything before any heavy boots or engines stir the dust. Cross-check every reading against independent instruments. If gravity and neutron and radar and seismic profiles all converge on the same patch, then the target is real, and it is worth the most careful excavation humans have ever attempted on another world. Which of these clues do you find most convincing? Do you lean toward the cautious geological explanation, or do you think there is something waiting down there that nobody has accounted for yet? Tell us in the comments.